All right, I am going to do a brief demo here showing how to use TeslaMax EM to solve for a guided mode in a silicon waveguide and then to show that mode going around a bend. So I'm going to start with TeslaMax website. I'm not going to assume that you have the software running at all. I'm going to do things from scratch. This TeslaMax website is teslamax.com. So you go here. I'll assume you've created an account and logged in. And so then you can go to downloads. If you have any issues creating your account or logging in, please email one of these addresses. Then go to download. And I've actually already downloaded this to save time, so you don't have to just sit here and watch my computer download. But let me just show you what I downloaded. I'm going to run this first on, I'm going to run the GUI on Windows with a CUDA locally. So I will want this one. This is in the Windows folder, x86-64 CUDA. If you don't have an NVIDIA GPU installed, then do not run this because it won't work. So I downloaded that already. I've extracted it, and I'll run it in just a second. I also downloaded the Linux version for x86-64 CUDA because I'm going to run this on a Linux machine as well in a moment to demonstrate running with a remote compute device with a local GUI. Okay, so here is the unpacked directory, and we're going to use this project file. It has some material stored. Let's jump right into it. So just double-click TeslaMax GUI. There it is. Okay, there is not any licensing information entered just yet. This is the same on this computer. I mean, this is the same information that you would enter on the web account. So enter that. That is when you log in up here for your account. Great. Okay, success. So software is now running, license is valid, etc., etc. So let's start. So first, I'm going to create a new project, call it modesolve. And I like to create my modesolves in a separate project from the actual simulation. And I'll show you that in just why that is in just a moment. Create a mesh domain. Just to make things run really fast, I'm going to use 0.02 micron discretization. For silicon photonics, generally this will be close. If you really want something precise, use 0.01. And you can use adaptive meshing too. I'll show that in another demo. And you can see there's sort of a scale and the units for most things that you enter. When you change the mesh, you need to just click on regenerate. There's a reason for this. It's kind of important. So let's just move on. I'm going to create a view 2D. All right, so let's take a look. We're in the XY plane. You can see the location. You can also see the grid points up here. We can actually do a bunch of stuff. Just look at this view window. We can actually even show the mesh if we want. Let's try that. Yeah, so you can actually see the grid points in the mesh. Makes rendering a bit slow, so we don't really need that most of the time. Let's create a simulation domain. The simulation domain is sort of the starting point for a lot of different types of simulations you might run. And we're going to need that materials project thing I was talking about. There we go. I'm opening this. And right now, because the software is in alpha, we really just have a couple materials to find. And, silicon and silica, we should take a look just very quickly. I'm using the field edit window. Let's take a look at the actual index as a function of frequency. So, all right, yeah, there we go. So, and in wavelength in nanometers, the index of refraction in n, that we are using this is defined over here. You can see different material variants are allowed. You could do, there are actually many different things, perfect conductors, lossy materials, anisotropic materials. But this is just a very simple model for silicon, frequency dependent, isotropic. So we'll use the field edit stuff for a lot of window for a lot of stuff, but for now, let's just close that. Okay, so I am going to specify a background material. I specified the silicon to be, actually, I want the silica to be operand 0, and then I'll go here and right-click this, and now I have this. If you wanted, you don't need to use this right-click operand 0 thing. You could simply enter in manually the value, but or you could do that with the Python bindings. But I always find it to be easiest to do this. That's why I set it up this way. And now the background material is going to be silica. So now let's create a simple waveguide. Okay. We need to set our insertion point to here. I could just create my structure in here, but you know what? Let's create a group called structure just to kind of partition my structural objects in here. So I will create a box. And I'm going to make my, actually first let's create the modesolve domain. So modesolve. I'm going to make it 4 microns wide by 3 microns tall. I think that's sufficient to capture the TE0 mode. What you want is you want something where the boundary will be far enough away that the field will go to 0. Okay, so now let's add a box. There's a bunch of different structural elements of varying complexity. And, you know, I didn't draw that very precisely because I was just going to use this to enter in the position manually. And I'm going to have 0.5 micron wide, 0.22 micron tall. Okay, it's not centered. It is centered, the bottom here is exactly at 1.5, but the center should be at 2, not 1.5. I don't know why I did that. All right. Now let's specify that this material is silicon. Okay. All right. Why don't we go ahead and save this project? We'll just call it modesolve. And I'm going to save it in the demo folder, not in the folder with the program, to keep things from getting confused. Okay, so we're actually, okay, before I worry about the cluster and everything, let's first figure out what we're going to do in terms of the modesolve. There's a couple of key things. The first thing is, right now the modesolver is set up that you select a range of betas, and then you solve for omegas for each beta. And it probably would be better to just select omega and solve for beta. This is how I've usually done it for a variety of reasons. One reason being that in this approach, you can solve for block modes, and this modesolver is capable of solving for block modes. But for a lot of things, for just continuously symmetric devices, it is easiest to have omega be the independent variable, so to speak. But anyway, here we are with the current design. It has 7 betas, and there's a frequency range specified. A key point here is I'm just going to ask for one mode. I'm just going to get the lowest mode. You can ask for as many modes as you like. It just takes progressively longer. Well, I don't know if it's going to converge if the number is like 7 or 8, but certainly 2 or 3, I've done that without any problem. And sometimes you really need to because you really care about the second order mode, like the TM0 mode, or maybe even the TE1 mode. And you can get all those things. Now, the one thing is if you select a frequency range whereby these modes don't really exist or are not well defined, the modesolver just may take a long time to run. And so I'm just going to leave this one. And then a fairly wide frequency range and a guess at what the effective index is, which then turns this into a beta. And so we will do that. Now I have to add the betas from range. And the reason for this step is now we have the betas that is specified. The reason for this step is that then, you know, you might have different ways of specifying the betas that you want. And so we need a distinct step. Here is the list of betas that it's going to solve for in the order that it will solve for. So this is in simulation units, and it is in radians per micron for this particular simulation domain. And you can see some information on the simulation domain and detailed status, conversion factors to go between E simulation and real units. When it solves for the waveguide mode, it'll be normalized to have a power of 1 milliwatt. In simulation units, that's just going to be 1. But then that allows you to back out what the actual field values would be. And E and H are going to scale as the square root of the power. So, okay. So we got this. I should add that the actual absolute value of E and H oftentimes do not matter. For example, if you're looking at bend laws, you really just care about the modal coefficient extinction as you go around the bend. Really, any problem in linear optics, even if there's loss, it's really not too important what the actual absolute units are. But I think it's good to know, just so that you have an intuitive sense for what's going on with the physics. So we've made an effort to make that very transparent. But at the same time, it's probably not usually something that you'd use. Okay, so we're all ready to do a mode solve. I'll just save the file here. What we now need to do is to specify our computation device. And the first thing I'm going to do, I'm going to go to sysinfo. And for compute, right now it specifies by default a compute GPU will be used. And that actually means that then when I created this mode solve, it too by default specified a GPU. So we're going to have to provide it with a cluster with GPUs. And we can do that by creating sort of a local cluster, which is just sort of a computational device to allow us to access the local GPU. I'm going to create a new project. I'm going to call it cluster. And now I will create a node, which is just a compute device to access the local machine. I have to define a few things. I have to create a cryptographic key. I'll just call this key. And I'm saving in the demo folder. Then I'll create a non-util instance ID and a node ID, which is a little bit cumbersome. This is left from an earlier version of the software, but you probably maybe eventually it'll just make it so automatically does that, because it's almost always what you'd want to do. Then you initialize. All right. Create cluster. Connect. And there's some error message, but in fact it's actually fine. That was just some starting up thing that it didn't detect. Yeah, so that's my local host name, Big Win Tom. That was not a reference to some massive victory. It was actually big Windows machine. This machine is kind of large and hard to carry around. Detailed status of this remote compute node. Let's see here. Yeah, here we can see a bunch of stuff about what's going on. I think the most important thing to look for is this. There's a CUDA device that's detected. We see what it is. We see how much memory it has. So this is all good. Another thing to look at is storage area. 1.6 terabytes free. The disk space will be used at times. A lot of it, potentially, if you have a lot of fields you've created. So we want to make sure that's available. Okay. So we're almost ready to run the simulation. I just set the operand and click on that. And that's actually it. We're ready to go. So let's see. I'm just going to start. And okay, it's running. Let us take a look. All right, it's coming along. There's our first mode. You can see there's a little preview window. We can see what the mode looks like. Can do normalization up here. Okay, I was zoomed all the way out or something. Yeah. Okay, so we have a node or mode at 1.4973 microns, and the effective index is 2.544, and it looks like what you'd expect for a Silicon Ridge TE0 mode. So I did, this is on the path to being correct, and I think I requested 7 betas, so we'll just give it a little bit of time to converge. While this thing runs, I have to add, this is not a great runtime for this mode solver, even though it's fast enough probably, such that the setup time will be longer than the mode solve time. This is not a great runtime for CUDA really should be like 200 gigaflops per second at least, I would say. Maybe not quite that fast, but that's something we're working on. But that being said, this is probably fast enough for a lot of things. Detailed status window. Yeah, you can actually look at the status of the modesolve and the eigensolve just to make sure, just to see what's happening by just clicking on the compute node. When we're running FDTD, you can do the same thing. You can see what's going on. And yeah, so while that modesolve finishes, let me demo just a few more things here. So let's say we wanted a closer look at the mode itself. We can do that, and the way we'll do that is we'll go and render it in this other window, which takes a little bit of doing. The rendering is set up to automatically work when it descends from an FDTD object, but in this case, it's a little bit complicated because it descends from a mode. First thing is we'll inform it that it's not descending from FDTD. So set auto render to none. Then we have to select the actual thing that we want to render. So I just set the modesolve to be operand 2 and the render to be operand 1. And this lets us just see what are the fields here that we have in our modesolve. And we can copy them over essentially, or copy the one that we want to see over. So you can see there's a bunch of different modes, and it lists the beta, the omega, also in simulation units. Let's select this one. Here. Here we had the frequency. This is in SI units, so that's convenient. And I think 1.55 is like close to 1.94 terahertz. So this will be close to 1.55 micron, very common wavelength. We're going to go to duplicate and copy by reference this thing. This field is a reference to this field is now copied to the rendering object, and then it renders. So actually we can see the field. We can do a contour plot if we would like. We can see the maximum field value in simulation units. Actually, you can look in SI units. And again, this is for 1 milliwatt normalization. And you can do a contour plot. Yeah, unfortunately, there's some noise in the edge, it looks like, but that's just some kind of noise. You can adjust the modesolve tolerance probably to get rid of that, but this is probably good enough for our purposes. Yeah, I actually don't know why the contour plot picked that up. There's very low amplitude out here. Well, that actually begs the question, just what was the amplitude of the field out there? Well, let's take a look. Actually, let's do a couple things. First, let's try measuring the power. And to that end, I'm going to create a power measurement device, pointing measure. Let's see here. And yeah, this is another one of these things where it automatically tries to detect. So we'll turn auto measure off, then set this. And let's again copy a reference to this field over. This will be what the pointing measurement thing measures, and then let's just do measure. Yeah, okay, so 1 milliwatt of propagating power. That would be the time average power of this complex field were you to take the real part of the complex field and average the power. So, because ultimately complex fields don't exist in nature. So that's the way to get back to real units. All right, so that's fine. So let's look at field measure. I'm going to measure the E field across this surface and plot it. So let's take a look at that. So I'm just going to do this, and let's see. Yeah, so the field measure has to be along an orthogonal axis. And what I didn't do here is I didn't draw it all the way to the end. Let's just drag that out. But now I need to get it back to the orthogonal axis. There we go. All right, so that should be good. That should give us a nice little cross section. We can plot the EX field as a function of distance. In fact, let's make this thing very exact here. Let's make it 1.6 and 4. I think it'll be okay if it goes right to the boundary. By the way, I'm going to save the project here. The modesolve is now done, by the way. We can see the entire plot. Yeah, there we go. That looks pretty reasonable. You can see that at longer wavelengths, the field starts to leak out more and more. And if we wished to do so, this would be a good guide to sort of lowering the frequency range to get the TM0 mode. Okay, there's some warning about the license server. I don't know why. It can be ignored. I think I know exactly what happened. My network is a little bit wonky here. I tried to make this software super resilient in the face of wonky network. So hopefully. All right. Oops. Yeah, this is the thing we want to measure. So once again, set this to operand 0. Copy by reference. Measure. And then actually we can plot it quite easily. We're going to plot component 0. You can plot a single component, a dot product, a bunch of other stuff, but let's just keep it real simple. We're going to plot x. So let's plot x. And we get both the real and imaginary part. So typically what the modesolver does is it normalizes each mode that it finds such that there's 1 milliwatt of power, and further it's maximally real for the largest component. And so we see that, you could rotate this by, a square root of I, and it would still be a valid mode, but it tries to make it as real as possible. And there you go. These are simulation units, but we can see the distance is SI, and you can see the simulation unit value. Now, if you wanted to recover the actual SI units, once again, you could look at the conversion factors here, and there you go. Those are the conversion factors. So I think I will leave it at that for this particular demo, because we've now run over 20 minutes, and this shows solving for a mode. The next demo, I realized at the start I said I was going to also do an FTTD simulation. Let me do that in the next video, because this is already dragged on a bit. Yeah, so I've shown doing a modesolve using a local compute device, and I went ahead and saved the file, and yeah, I will leave it at that. Okay, thank you.